Today we're going to talk about infinite geometric series. So in the past couple lessons we looked at a geometric sequence and series. In a geometric sequence we're looking at a sequence of numbers where we multiply by the same thing as we move through each step. Then in the last lesson we talked about a series is where we add all those things up. Sometimes when we do this forever, that's what infinite means. So if we would add up the terms forever and ever and ever and ever and ever, it's just going to keep getting closer and closer and closer to some number. Sometimes it'll just keep getting bigger forever, and then we wouldn't really care so much about those. So a rule that lets us know whether or not it's actually going to add up to something is if the absolute value of r, or our ratio, is smaller than 1. So here's kind of two examples that show different things that could happen. Let's say that I start with a series that's going to begin at 2, and I multiply by 2 each time. So then I have 4, 8, 16, 32, etc. If I start adding these things up, it's just going to get huge, right? And then I'm going to be adding bigger numbers and bigger number and bigger number and bigger number, and it's just going to keep on getting bigger as a sum. As opposed to, if I took a series that starts at 2, and instead of multiplying by 2, I multiplied by like a half. Then I'm going to get 1, and then a half, and then a fourth, and then an eighth, and then a 16th, and then a 32nd. And these fractions are getting really tiny. So tiny, in fact, that eventually it's like I'm basically adding 0, and we're just going to say at some point it just kind of stops mattering that I'm even adding things to this, and it's going to add up to some number. Okay? And the rule that lets us know what it's going to add up to is this rule in the front. S means sum, so this says that our sum is equal to a sub 1. What does a sub 1 mean? The first term divided by 1 minus r. Okay? And this only works if that ratio, what we're multiplying by, is smaller than 1. Because if it's bigger than 1, then these things are just going to keep getting really, really big and add up bigger and bigger and bigger. It's just going to keep on getting bigger. Okay? So if that ratio is smaller than 1, so a fraction like a half, then we can perform this formula. So in this case up here, our sum is equal to, first term is 2 over 1 minus a half. So this would be 2 divided by 1/2, which is 4. So that means if I add up all the terms of this forever, it's just going to keep on getting closer and closer and closer and closer to being 4. Which is kind of crazy, because we're already almost there within the first few terms. So we add up, and then we've got 3, and add that. Now I'm at 3.5, 3.75. I'm like almost already there, and I'm not even very far into this. So then it becomes that these fractions are just so small that it just really doesn't make that big of a difference. Okay? But this only can be done if what we're multiplying by is a ratio smaller than 1. Okay? You could do this formula on that first one, and it'll give you an answer, but it's going to be wrong. Okay? It just doesn't work. Okay? So you should only do this if our ratio is between -1 and 1. It can still be a negative ratio, but between -1 and 1. Okay, so always check your ratio before applying this formula. So here, find the sum of this infinite geometric series. So we're in the sigma notation, and we can see at the top that we're going from 1 up until infinity. So first thing we need to do is think about what is the ratio of this series. And where do we locate that? The 0.7 is our ratio. The ratio is the part that's taking on the power, because what a ratio means is that we're multiplying by this thing over and over and over, and that's what powers do, is tell us to multiply by something over and over and over. So the base of that exponent is always going to be our ratio. So our ratio is 0.7, which is smaller than 1. So that means that this one will add up to something. So what is it going to add up to? So our rule is that the sum is a sub 1 over 1 minus r. How do I find a sub 1?
Plug 0 in.
We're going to plug in whatever's at the bottom. Okay? A sub 1 means the first term of this series, which is plugging in the bottom value into the rule. So it's going to be 3 times 0.7 to the 1 minus 1. 1 minus 1 is 0. 0.7 to the 0 is 1. So that gives us 3 for our first term. And then R, we said was 0.7. So that gives us 3 over 0.3, which is 10. So that means if I added up all the terms of this thing forever and ever and ever for the rest of my life, and then I told my kids, like, guess up when I die, you have to keep on adding up terms of the series, we would just keep on getting closer to 10. We're never going to get past it, and we're never actually going to quite get to 10, but we're going to get so close that it's like 9.9999999, and we say we're just going to call that 10. All right, what is the ratio of this series? What are we multiplying by as we move through here? 4 on the bottom, so it's really like 1/4, and what else is happening?
Adding,
Every time we have that positive negative flip, which means we're multiplying by a negative 1/4. So if I multiply 1 times negative 1/4, I get negative 1/4. Times a negative 1/4 gives positive 1/16. So our ratio here is a negative value because we have that positive negative flip happening. That still meets our criteria. It's between negative 1 and 1. So we can apply our sum formula. So sum is equal to a sub 1 over 1 minus r. A sub 1 means first term, which is just 1. 1 minus r, which is negative 1/4. 1 minus negative 1/4 is 5/4. How do I divide by a fraction? Multiply by the reciprocal. So this is 1 times 4/5, which is just 4/5. Now this one's actually going to bounce back and forth because of that negative. So if we started looking at what things add up to, if I add up the first two, I get 0.75. Oh, and then I'm going to need a calculator. I can't add that in my head. What am I thinking? So if I add 1/16 to that, I get 0.8125. And then if I add up the next one, what's going to happen is it's going to bounce back under. Because this 4/5 is really equal to 0.8. So what's going to happen is each time as we add or subtract, it's just going to kind of bounce back and forth around it. So it's a little bit smaller than 0.8, then it gets a little bit bigger. Then it'll get smaller again and bigger and smaller and bigger. But it's going to keep on getting closer and closer and closer to being 0.8. So like visually what we would see if we would plot the points is like it's smaller if this is 0.8. It's smaller, it's bigger, it's smaller, it's bigger. But those distances are going to become less and less so that it's going to kind of like zero in on that line eventually. Okay. So it's okay to have a positive ratio or a negative ratio as long as the value of the ratio is smaller than 1. Okay. Ignoring the negative or positive, as long as the value, the absolute value of it is less than 1, we can apply this rule. Go ahead and try this one and the next one. All right, so what is our ratio on this one? 0.1 is our ratio. Whatever has the power is going to be our ratio. That meets our criteria being smaller than 1. So our sum is a sub 1 over 1 minus r. A sub 1 we find by taking whatever's on the bottom and plugging it into the rule. When we do that up in the exponent, we get 1 minus 1, which is 0. 0.1 of the 0 is 1, times the 2 out front, and we get 2. Then over 1 minus 0.1, we get 2 over 0.9, which is 20 over 9. As a decimal, this is a repeating decimal, so it is better to leave it as a fraction. It's 2.2 repeating. But when we get a repeating decimal, it's best to just leave it in its fraction form. The easiest way to get it there is I just wanted to get rid of this decimal that was on the bottom. So I moved it over 1 spot, which means I need to move it over 1 spot on the top as well. So I just turn the top into a 20 and the bottom into a 9. What is our ratio on this one? 1/3. So each time we're dividing by 3, So then we'll think about multiplying by 1/3. So that meets our criteria. A sub 1 is 12. 1 minus 1/3 is 2/3. And we divide by a fraction by multiplying by the reciprocal. And that gives us 18. So that means if I add these up forever and ever and ever, it's just going to keep on getting closer and closer and closer to being 18. And we can see we're already getting pretty close after just a few terms. So 12 and 4 makes 16. And then the next one would give us 17 and 1/3. And we're already getting pretty close. And we're only 3 terms in.
Do we have to reduce the fractions? Like,
They
we
should be
done?
reduced. Yeah. Yeah, they should be reduced. An infinite geometric series has a first term of 4 and a sum of 10. What is the ratio? So our formula is S is equal to A sub 1 over 1 minus R. And by the way, again, this formula, as with all the other ones that we've had in this chapter, does not need to be memorized for the test. We are told that A sub 1 is 4, so we can plug that in its spot. And we're told the sum is 10, so we can plug that in the spot for S. And then we need to solve this equation for R. To do that, I'm going to multiply both sides by 1 minus R. I'm going to distribute the 10 over there. Subtract 10 from both sides. So negative 10R is negative 6. And divide by that negative 10. So R must be equal to 3/5. When you're solving these, you must get an R value that meets our criteria. So if when you're solving this you get an R value that is not between -1 and 1, you must have done something wrong at some point. Because the only way that it could have a sum is if that ratio is between -1 and 1. So you can kind of use that as a checkpoint for yourself. If we had done something backwards here and say, for example, we got 5/3, we could know that's not going to be a right answer because that's bigger than 1, and that ratio needs to be between -1 and 1. Questions? Go ahead and try this one. Alright, so this one, we're going to use our sum formula. We're told that our sum is 27 over 5. Our A sub 1 is 5. And we're looking for R. And we could solve this one exactly like the last problem and multiply both sides by the 1 minus R, and that's a totally fine way to do it. But another option in this one, because that sum is a fraction as well, here we have a fraction equal to a fraction, which is known as a proportion, and that can be solved by cross multiplying. So then I get 27 times 1 minus R is equal to 25. If you just multiplied both sides by the 1 minus R, that's totally fine, it'll work. I just like doing this because now I don't have any fractions in my problem anymore, so it makes things a little bit cleaner for a while. Then I'm going to distribute the 27. I'm going to subtract a 27 from both sides. And then I'm going to divide by a negative 27. And I then get that R is equal to 2 over 27, which should be the same thing you got if you just multiplied both sides at the bottom by 1 minus R as your very first step. Just this way, I didn't have to worry about fractions again until the very end, and otherwise you would have had to kind of keep on working with that 27 over 5 all the way through. It's a little bit uglier, but it should result in the same answer if you do all the arithmetic right throughout the problem. Questions? Alright, our last kind of problem kind of answers a question of why we've been able to do something all along that you maybe have never thought about or never really care. But all along I've kind of asked that if you have an answer that's a repeating decimal, that you turn it into a fraction. So I said if it's a nice clean decimal, you can just kind of leave it as it is. But if it's a repeating decimal, then it's best to give that kind of an answer as a fraction. So our next kind of problem looks at, well, why can we always do that? Like, why will every single repeating decimal be able to turn into some kind of a nice fraction? In terms of actually solving this, you could totally take your calculator and type in 0.181818 for a while, and then have your calculator turn that into a fraction. It'll give you the answer. But really, math, I think, is a whole lot less about computation, because computers and calculators can compute. That's not really what math is all about, but more in understanding kind of why and how things work is the bigger ideas of math. We don't need people necessarily to be good computers, because we have computers and calculators. We need people to be good thinkers and question askers. So we're going to look at why these decimals can always be turned into fractions. And the reason, maybe surprisingly, is because of this idea of infinite series. So the decimal's infinite. It goes on forever and ever. So what I want to do is write it as an infinite series. And I would do that by breaking it up at each repeat. So I'm going to take that 0.18, and there I hit a repeat. I'm going to say plus. And then whatever I would need to add to make it hit the next repeat. So I would need to add a couple of zeros as placeholders, and then another 18. And then I would need 4 zeros as placeholders before the next 18. Okay. So then if I put all these together, the 18s would line right up into those zeros, and I would get this 18, 18, 18, 18 forever. So now that's a geometric series. So we should be able to do our geometric series formula. S is equal to A, first term, over 1 minus R. And R is the common ratio, which can be kind of hard to see when we look at these. But remember we talked about, when we first talked about geometrics, one way to find a ratio is always to take a second term and divide it by a first term. And so we could do that division out and we get 0.01. So then we get 0.18 over 0.99. And I kind of alluded to this on our very first example, but the easiest way to get rid of the decimals in this problem is just think about how many times do I need to move them. So on the top, I would need to move it twice. On the bottom, I would move it twice as well. And so this thing can just turn into, with no decimals, 18 over 99. If we reduce, those both reduce by 9 to leave 2 over 11. And if we would type 2 over 11 into a calculator, we would see that that's 0.18, 18, 18, 18 forever. So the reason why we can take every repeating decimal that could happen and turn it into a fraction is because of this idea of infinite series. Alright. I'm going to skip this next one because something a little bit weird happens on that one, and I don't want to worry about that right now. But on this very last example, if I want to break this up into its repeats, to get to the first repeat, I would need 0.027 plus, then the next one, since this had 3 digits in it, I'm going to need 3 zeros to cover those up, and then the next repeat of 27. That has 5 digits, so then I would need 5 zeros, and then the next 27. And so on and so forth. So if I would line those all up, then we would get all the 27s in their appropriate places. So then we can do A over 1 minus R. First term is 0.027. 1 minus. To find R, you can always take your second term and divide by your first term. Once again, this time we get 0.01.
Will you always get 0?
The reason why we got 0.01 this time for both of them is because they were both 2-digit repeats. If it was only a 1-digit repeat, like 0.33333, then we would get 0.1. If it was a 3-digit repeat, like 0.123, then we would get 0.001. So there is a pattern to why we get those decimals that we get, and it's how many digits there are in the repeat. So here I get 0.027 over 0.99. If we do this move the decimal trick, if I move it 3 times on top, I need to move it 3 times on bottom as well, which means I need an extra 0 there. So this is going to turn into 27 over 990, which both of those can be reduced by 9 to give 3 over 110. And if we type 3 over 110 into a calculator, it should give us the decimal that we began with. Alright, so your homework tonight is from 11.4.